Section 3.5 goes over the real zeros of a polynomial function. Now, this is a section that I've added that I haven't gone over in the past, but when I was in your shoes, we went over this stuff, and it did make calculus a little easier in places, so I feel inclined to include it this semester. What we're going to do first is look at the division algorithm for polynomials. We've already, just today in answering the homework questions, we've divided polynomials to try and find the oblique asymptotes. Do you remember doing that? Okay, so when we did that, we ended up the ratio of two fractions, as long as the denominator is not 0, would be another polynomial equation, plus the ratio of a polynomial equation where r of x is the remainder and g of x is our divisor. It's what we divided. So f of x we call the dividend. When we divided, f of x was inside the house, so it's in dividend. And then g of x is our divisor. It's what we were dividing. And then we ended up with a quotient, q of x, that was a polynomial, plus some remainder, r of x, that we put over g of x. So it's possible to take a ratio or a rational polynomial, rewrite that function as a product of the quotient and divisor plus any remainder, which leads us to the remainder theorem. Let's let f be a polynomial function. If f of x is divided by x minus c, then the remainder can be found by just plugging in c into the function. This is a theorem that we present without proof. Just know that if you're dividing by a linear factor, the key here is you have to be dividing by a linear factor, and the leading coefficient has got to be 1. So that's critical in order for this remainder theorem to work. The factor theorem follows closely along the heels of the remainder theorem. It says let f be a polynomial function. Then if we have x minus c that's a factor of f of x, that's the case if and only if the remainder is going to be 0. So if the remainder is 0, we've found something that's actually a factor of the function. Because if we had a remainder that was 0, then we've got our factors. Because we can write this function as a product and there's no remainder. And these would then be the factors. Alright, so let's look at a problem then. We're going to use the remainder theorem to find the remainder if we divide f of x by x plus 2. I need to look at f of what in order to do part A. Part A here, the answer would be f of what? Well, I need to write this in the form x minus c. So I could rewrite this as x minus what? Negative 2. Subtracting a negative is the same thing as adding. I need to find f of negative 2. So that's going to give me negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 minus 1. Negative 2 cubed is negative 8. Negative 2 squared is 4 times 3 is 12 minus 4 minus 1. So there's 8, 9, 13. Looks like this is going to be negative 1. And then part B. How would we answer part B here? We need to find f of positive 1 because this is already in the form x minus c. So c in this case would be 1. The minus is part of this formula. That's an important thing to notice. So that's going to be 1 cubed plus 3 times 1 squared plus 2 times 1 minus 1. So that's 1 plus 3 plus 2 minus 1. It looks like this is going to be 5. Now, you can go ahead and do this using long division and just see what you get for the remainder. Probably wouldn't hurt for us to do one. Let's just do a check. Which one of these do you want to divide by? Let's do A. We'll do our check with A just to make sure that we get this right. So what number goes on the outside, or what polynomial goes on the outside here? It's x plus 2, and then inside is going to be x cubed plus 3x squared plus 2x minus 1. So that's going to give us x squared. So that's going to be x cubed plus 2x squared. And then I need to change my signs and add. So those terms right here are going to cancel out. 3x squared minus 2x squared is x squared plus 2x. We'll bring down the 2x. X squared divided by x is x. So that's going to give us an x squared plus 2x, and we subtract, which means that we're going to change our signs and add, and these are going to cancel out, are they not? X squared minus x squared zeroes out, and 2x minus 2x cancels out. We bring down the negative 1, and guess what? That verifies what we got for our answer. So what this does is it saves us some work in figuring out what the remainder is, and if the remainder happens to be 0, we would have had 2 factors, and that's what the factor theorem says. Because in the formula, or in the theorem here, it has to be linear and in the form x minus c. The minus has got to be there. In order to use the remainder theorem, you have to divide by x minus c, and the minus here is part of this formula. It's got to have the minus. Okay, so if you have a plus, x plus 2, not only does the leading coefficient have to be 1, you have to have a minus there in part of this. So if you have a plus, you're going to be using the opposite number there for c. You have to rewrite that so that the leading coefficient was 1. Next, we're going to look at the factor theorem. It says use the factor theorem to determine whether the function has the factor of x plus 1 or x minus 1. The factor theorem just says that if the remainder is 0, then we've found a factor. That's a quick way to check and see if you've found a factor. So let's do part A here. What we want to do is find the remainder, or check the remainder, f of negative 1. Why am I saying f of negative 1? You have to rewrite that as x minus a negative 1. The minus is part of the formula. So to find f of negative 1, we're going to look at f of negative 1 is equal to negative 2 times negative 1 cubed minus negative 1 squared plus 4 times negative 1 plus 3. So negative 1 cubed is negative, a negative times a negative is a positive 2, minus 1, minus 4, plus 3. This remainder is going to be 0. So is x plus 1 a factor of this cubic function? Yes, it is. So if we were asked to factor this cubic function, I know that I could divide that by x plus 1, and then it would work it down into a quadratic. The reason we want to do this, or know how to do this, is because it's very difficult to factor polynomials of degree greater than 2. We have the quadratic formula to help us factor quadratics. There's even a complicated formula for factoring cubics. But anything above a 4th degree or higher, there's no set or pat formula we can use in order to factor those polynomials, even though they all factor into a product of linear and quadratic factors. The fundamental theorem of algebra teaches us that, and you get into that in grad school. It is possible to factor every polynomial into a product of linear and quadratic factors. That doesn't mean we know how, we just know it's possible. And mathematicians have proved that. It's a well-proven fact. This gives us a way to narrow down what those factors might be. So since I know this is a factor, what I could do then towards factoring this is I can actually take this polynomial, negative 2x cubed minus x squared plus 4x plus 3, and divide it by x plus 1. So when I divide this by x plus 1, I'm just going to do this really quick. We get minus 2x squared, and that's going to give us a negative 2x cubed minus 2x squared. Change the signs and add, and that's going to give us 0. 2x minus x squared is x squared. Drop down to 4x. So this is going to be plus x squared plus 1 plus x, change the signs and add, so this now becomes subtraction, minus, and that's going to give us 4x minus x is 3x, bring down the 3, and we see that this is going to go 3 times, and we get our remainder of 0 here. So we know then that we can rewrite this cubic function as x plus 1 times negative 2x squared plus x plus 3. Now we have the quadratic formula to factor this, so that's a step towards factoring that cubic function. That's the reason we wanted to know how to do this. We still have to do part B here. Is x minus 1 going to be a factor of this? How do we check to see if x minus 1 is a factor? I need to find f of 1. I can just look at this, and that's going to give us negative 2 minus 1 plus 4 plus 3, and that's going to be equal to 7 minus 3 is 4. Is this a factor? If you have a polynomial, remember we said that it can have at most the degree, the highest degree as the number of zeros. So a cubic can have at most 3 zeros. A fifth power can have at most 5 zeros. A quadratic can have at most 2 zeros. So that's going to come in handy whenever we try to find how many zeros something has. We are also going to use something called Descartes' rule of signs. And this comes in handy as you try and narrow down possible factors of polynomials. We're going to let f denote a polynomial function that's written in standard form. So we have ax to the n plus bx to the n plus 1, so forth and so on. The number of positive real zeros of f either equals the number of variations in the signs of a non-zero coefficient, or else it equals that number less an even integer. Let me show you what I'm talking about. If this is our polynomial function, we see that we go from positive to positive, not a sign change. Positive to negative is a sign change. That's positive to negative. And then we go from negative to positive right here. So there's a total of 2 sign changes, one here and one here. So there can be at most number of negative real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of negative x, or else it's equal to that number less an even integer. So right here, if I wanted to find the number of negative zeros that are possible here, I would have to look at f of negative x. If I replaced x with negative x on a fifth power, this term would become negative. So this is negative 5x to the fifth. This would stay positive, plus 2x to the fourth. And negative times a negative would become positive 3x cubed. This would stay negative, 2x squared. This would be plus x plus 4. So we count the number of sign changes here. So we go from negative to positive, positive to negative, and negative to positive again. So there could be either 3 or 1 negative real zeros. Now the reason this comes in handy is because we have a way of ruling down what those possible rational zeros are. This is called the rational zero theorem. If we have f be a polynomial function of degree 1 or higher, and it's in standard form, where each coefficient is an integer, if p over q in its lowest terms is a rational zero of f, then p must be a factor of the constant, and q must be a factor of a sub n. I just remembered calling this as a student P over Q, because that's what it dealt with, was P over Q. P are the factors of the constant, Q is the factor of the leading coefficient. So if we want to list all possible potential rational zeros, which is what this gives us, it gives us numbers that we can plug into the function and use the factor theorem to see if we found the zeros. It narrows down our choices for factoring of what these factors would be. So the potential rational zeros of this we can find by looking at the ratio of p. P will be all possible factors of negative 12. Well, that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. These are all possible factors of negative 12. Because I can take a positive 1 times a negative 12 and get a negative 12. Or I can take a negative 1 times a positive 12 and get a negative 12. So P is going to be all of the possible factors of this constant function. And Q then will be all of the factors of 3. So that's going to be plus or minus 1 and plus or minus 3. It helps that that's prime because we have fewer choices. So then to list all the potential zeros, we look at the ratio of P over Q in its reduced form. So P over Q is going to be all the potential zeros. That's going to be plus or minus all of these numbers over 1 plus all of these numbers over 3 in their reduced form. So that's going to be plus or minus 1/3, plus or minus 2/3. I don't list 3/3 because 3/3 reduces to 1 and it's already listed. Plus or minus 4/3. I don't list 6/3 because 6/3 reduces to 2 and it's already listed. And nor do I list 12/3 because 12/3 reduces to 4 and it's already listed as well. So this would be the list of all potential rational zeros. Well, that's a lot of numbers. I can tell using the Descartes rule of signs how many of these roots will be positive and how many negative. You can use the factor theorem in order to find these zeros. Well, that's what we're going to do with this next example, which fortunately is the same function, so we've got all of our potential candidates here. What is the most number of zeros that we can have? We notice the degree of this polynomial is equal to what? So that means we can have at most 3 zeros. It's possible we could just have 1, because this cubic function could do that, and then we would only have 1 zero. Or it could do something like this, and we would only have 2 zeros. Or it could do something like this, and we would have all 3 zeros. So what can I do next then in order to make progress toward finding these? Well, I've got all of my potentials here, and we're trying to factor this out, so I need to know what numbers I should check to see if they're a factor. What we need to do first maybe is check and see how many zeros we have. How many positive zeros will we have? We change signs from positive to negative once. We're going to have 1 positive zero. What about negative zeros? Well, maybe we should rewrite this and find f of negative x. That's going to give us a negative 3x cubed plus 8x squared plus 7x minus 12. So how many negative zeros? There's one sign change and another sign change. We could have 2 or none. Let's check the positive zeros first. Here's a possibility. The question was, how is there a possibility that there's 0 negative? If our function does this, we know it's increasing. It could have a positive 0 and no negative zeros, like this. It only has 1 0. It's not going to do something like this, where we only have 1 negative 0. We know that's not a possibility. We're either going to have 2 negative zeros or no negative zeros. So that means that our graph, I know it's going to be increasing because the leading coefficient, it's going to look something like that, or it's going to just have 1 positive root. That's what Descartes' rule of sign tells me. So it tells me whether or not I should focus on positive or negative numbers. So what I'm going to do is I'm guaranteed a positive 0. I'm just going to plug in positive 1 and see what happens. So that gives us 3 plus 8 is 11, minus 7 minus 12 is negative. It's not going to be 0. So I'm checking to see what f of 1 is. That didn't work. What about f of 2? 2 cubed is 8. 8 times 3 is, so that's a positive 24. I'm just checking f of 2. So that's going to be 24, and then 2 squared, that's going to be 32. Minus 14 minus 12, that's going to be positive, so I know that's not a possibility. But this is what you do. You just take these numbers. Let's try a negative 1 and see what that gives us. F of negative 1. What I'm doing is I'm checking to see, and this can be quite a tedious task. So let's try f of negative 1. So that's going to give us negative 3 plus 8 plus 7 minus 12. 12 and 3 is 15. That looks like we found one. We have a negative, so that's going to be equal to 0. So what's going to be a factor? Because of this remainder is 0, what's a factor? X plus 1 is a factor of 3x cubed plus 8x squared minus 7x minus 12. Once we have one factor or a cubic, we can divide and work it down to a quadratic. And then if we don't see how to factor what remains, what's going to help us out? Quadratic formula. So I take x plus 1 and I see how it goes into 3x cubed plus 8x squared minus 7x minus 12. So when I divide here, what do I get? 3x squared. 3x squared times x is 3x cubed. 3x squared times 1 is 3x squared. Change the signs and add, and that's going to give us 8 minus 3 is 5x squared. Bring down the minus 7x and divide, we get 5x. So 5x times x is 5x squared. 5x times 1 is 5x. And we subtract, which means we're going to change the signs and add. So negative 7x minus 5x is negative 12x, and then bring down the minus 12, and it looks like this is going to go minus 12 times. So how can I rewrite this polynomial function at this point in its factored form? Parentheses x plus 1 times 3x squared plus 5x minus 12. Is this going to factor? I think so. Let me see if I can just do it using reverse FOIL. Let's try 3x and 3. That'll give us 9. Minus 4 is 5. So we want to have a positive 9 minus 4. I think that'll work. So we've now found the factors. So we end up with 2 negative zeros and 1 positive 0 for this function. This is the way we would factor. And before the world of graphing calculators, this is what we had to do. So it looks like 4/3 was our positive factor, and negative 1 and negative 3 were the negative factors. Rather than trying to factor this quadratic, you could have used the quadratic formula, or you could have kept going with this factor theorem and see what function or what factors have a remainder of 0 as well. Just remember that this factor has got to be in the form x minus c. So you're going to plug in the opposite sign of the number that you're checking. So that's why if we're checking negative 1, x plus 1 gave us the factor. And that wraps up today's lesson. There is a summary now of these steps that you can read and go through, and it will be available on the note.